Okay, because the case where you do have linear terms resulted in a paraboloid, but we understand how to deal with the parabolic direction, how to find it. We understand what the cross sections look like. Okay, and we understand that there are other cylindrical directions as well. We know how to find those as well. So it all boils down to analyzing what happens among the u-axes, the span of the u-axes, where we have no linear terms at all, just pure square terms. Okay, so as I said before, that is going to depend on the signs of the lambdas and also on the sign of q. Okay? But the first thing it depends on is whether q is 0 or not. Okay, because that makes a major difference. Yeah, so let's first look at the case where we have where q is 0. This is, I guess you can call case 1a. All right, so then the equation looks like this. And everything is going to depend on, again, the signs of the lambdas. All right. Oh, notice that none of the lambdas are 0 by construction. You know what? It's probably better to consider this case first, when q is not 0. Okay, anyway, so if q is not 0, what I'm going to do is just divide through by q. So all the coefficients will pick up a factor of 1 over q, and then there will be a 1 on this side. Okay, so I'm just going to rename the coefficients for simplicity's sake. So let me call the first coefficient like mu1. Oh, I guess that's too close to u. Lambda, just use lambda. Okay, how about kappa 1? Okay. It's hard finding distinct notations for everything you want. All right, anyway, so I have this equation now. This is sort of the standard form of case 1a, where the constant q is not 0. All right, so we have a 1 on, like, by itself, isolated on one side of the equation, and then we have this linear combination of pure square terms on the other side. And notice that none of the kappas are 0, because none of the lambdas were 0. So no kappa j is 0. All right, great. So what can we say about this? Well, there are a number of things that can happen. First of all, subcase 1a1, let's say all the kappas are positive. Kappa 1, kappa 2, kappa r are all positive. Right? Then we get what's called an ellipsoid. This case is called an ellipsoid. Right, and we can write kappa 1 in the form like 1 over a1 squared by just defining a1 as the square root of 1 over kappa 1 by definition. And similarly, kappa 2 can be written in the form 1 over a2 squared by defining a2 as that. Okay, because kappa 1 is positive, this makes sense. This is a real number, and in fact a non-negative real number, as is this. Okay, and so on and so on. And then you put the equation in the standard form of an ellipsoid, which is u1 squared over a1 squared plus u2 squared over a2 squared. And then ur squared over ar squared equals 1. Right? That's like the standard equation of an ellipsoid in standard position. And this is, remember, in R space, with the axes labeled u1, u2, etc., up to u sub r. Okay. And you can see that it has a center, which is just the origin of R space. So what I mean by this is just that any point that's like on the set, let me call it capital E for ellipsoid, has the property that minus u1 up to minus ur is also in the set. So it's like, that's like a point reflection through the origin. Okay. Anyways, you see that that's true. It's clear. So it does have a center, and then also we can interpret the numbers a1, a2, and so on as like semi-axes. a1 is the semi-axis in the u1 direction, and so on. Okay, and you see that that's true because if I set u2 and u3 and ur equal to 0, then the equation reduces to u1 squared over a1 squared equals 1. In other words, u1 is plus or minus a1. So what that tells you is that the points plus or minus a1, comma 0, comma 0 are on this ellipsoid. And of course, the same will be true of the points like that. And similarly for all the dimensions. Okay. Now I guess that doesn't really tell you that they're semi-axes. In some sense, like those are more special than is indicated by just these facts, although these facts are clearly true. But they also represent sort of axes of symmetry, in the sense that, for instance, if you take the u1 axis and look at the perpendicular r minus 1 dimensional space to that, that's like a hyperplane of symmetry. The reflection where you just, okay, so I'll say it this way. If I consider the mapping that sends u1, u2 up to ur to the point minus u1, u2 up to ur. So just u1 is negated. That's a reflection through the u2, u3, and so on hyperplane. Well, that reflection preserves the set E, just maps E back onto itself, simply because replacing u1 by its own negative and leaving u2 alone and u3 alone and so on clearly preserves the equation. Okay, so yeah, the semi-axes, the lines that which are simply the axes of space. The axes of space are axes of symmetry in this sense. So just like in 2 dimensions, you're very used to this from 2-dimensional case of the ellipse. So all the same stuff. Okay. So that's what happens when all the kappas are positive, strictly positive. Get an ellipsoid. It's very easy to understand. For example, you can take 2-dimensional traces, and they will be ellipses. So, if I look at the trace in the u1, u2 plane, that means setting u3 equal to 0 and u4 equal to 0. Then it'll just reduce to this equation, which is exactly the equation of an ellipse. And you can do that for any 2 of the variables. So all of those 2-dimensional trace families are just ellipses. Okay. Also, it's not just in those planes. It's in planes parallel to those. So for example, if I set u3 not equal to 0, but just equal to some constant, set u4 not necessarily to 0, but to some constant, then what that does is it takes all these terms and renders them constants, which I can then move over and combine with the 1. That will give me some new constant on this side, c, which, as long as it's not 0, you can divide through by that c again to get a 1 on that side again, right? And that will still give you an ellipse. So, good, that's what happens. Now, what if the c does come out to 0? So let me just make it clearer, make it a little clearer what I'm doing here. I'm saying, yes, this will be an ellipse, clearly, right? Which is the trace in the u1, u2 plane, where u3 is 0, and u4 is 0, and u5 is 0, and so on. But what about if I just take a plane parallel to that? So u1 is left a variable, and u2 is left a variable, but u3 is not set to 0, it's just set to some constant, and u4 is set to some possibly different constant. So what that does, it takes all the terms of the equation, other than the first 2, and makes them constants, which can then be moved over and combined with that 1. That will give some c on the other side. So in other words, it will be like u1 squared over a1 squared plus u2 squared over a2 squared equals c. Now what I'm saying is, if c is not 0, then you can just divide through by c, and that will just be the equation of an ellipse again, just with different semi-axes. The semi-axes then will be, you'll have something like this, radical c times a1 squared. And then here you'll have radical c times a2 squared, right, equals 1. That'll still be an ellipse. But what if the c is 0? What happens then? Well, in that case, what happens is that you just get a single point, because you see that you have like 2 non-negative terms here. These are both non-negative terms. So if their sum is 0, then they're both just 0. And the only way that can happen is if u1 and u2 are both 0. So you'll just get a single point in that case, which is, so you can think of as like an ellipse that's collapsed into a single point. If you take an ellipse and shrink it, make it smaller and smaller, when both semi-axes hit 0, then the ellipse collapses to a singleton set. So, but you see that it's not just the intersection curves in the coordinate planes, such as the u1, u2 plane, that are ellipses. It's actually the intersection curves in any plane parallel to those coordinate planes, 2-dimensional coordinate planes. And so that's the relation between ellipses and ellipsoids. The ellipse, as a 2-dimensional curve, very familiar 2-dimensional curve, appears as like the trace families in 2-dimensional coordinate spaces, 2-dimensional coordinate planes, in an ellipsoid. And it's not just the coordinate planes, it's all planes parallel to the coordinate planes, as long as they're 2-dimensional. Okay, good. So that's pretty much complete analysis of the ellipsoid. All right. Now, another easy case, which let me just dispose of very quickly by calling it 1a2, is the case where all the kappas are negative. All r of the kappas are strictly negative. See, that case is so easy, and you can just dispose of it because the solution is the empty set. That's what the graph looks like in that case. You see, because if every kappa is strictly negative, then this whole side will be like less than or equal to 0. You can make it exactly 0 by taking all u1 and u2 and so on and ur to equal 0. But you can't make it any greater than 0. So something less than or equal to 0 can't equal 1. And therefore, there are just no solutions in that case. Now, the empty set is a pretty easy set to describe geometrically. It's just not there. So we're done with that case. So what's left over? Well, we have the case where all the kappas are positive. We have the case where all the kappas are negative. What's left over is a case where some of the kappas are positive and some of them are negative. Right? At least one of each. And let's call that 1a3. So case 1a3 is where some kappa i's are positive, some are negative. All right? And by making a permutation of the axes, we can assume that like the first few kappas are positive and then the last few are negative. Yeah, by permuting the axes if necessary, which again, remember, is like a rigid motion. Okay, it's actually, I shouldn't call it that. It's not really, you shouldn't think of it as a motion, but it is an isometry. It preserves distance. If you just relabel the axes, then no distances will actually change. All right, so by permuting the x's if necessary, we can assume that, let's say, the first few kappas, kappa 1 through kappa, notations. Oh, let me just say m, are positive. And then kappa m plus 1, kappa m plus 2, up to kappa r are strictly negative. Okay, so here m is somewhere between. It's like at least 1, and at most r minus 1. So that there are some positive ones and also some negative ones. Okay. So then what happens is that the equation, remember we're working with this equation right here. Well, okay, I guess I probably should write it like this then. So it's kappa 1 u1 squared up to kappa m um squared, and then you can factor out a negative from all the rest of the terms. And all the rest of the kappas are negative, so I'll write them in terms of their absolute values so that I get positive coefficients. But you see that I factored out a negative from all of them, so it's correct. And the whole thing is set equal to 1. All right, well, something like this, where you have two groups of terms, both non-empty, right? This has some terms in it, and also this group has some terms in it. And they both have positive coefficients, right? This has all positive coefficients, and this group also has all positive coefficients. Notice they're strictly positive, because none of the kappas can be 0. So these are, coefficients in both groups are strictly positive. But there's a minus sign between the two groups. And then there's a 1 on the other side. Okay, an equation like that is called a hyperboloid. The graph of the equation is called a hyperboloid. Okay, so we've now encountered several terms. Let's just recall, we've encountered the term paraboloid. That's when you have some linear terms left over with non-zero coefficients. And after a rotation, you can make it so that there's just one linear term, isolated on one side, and then all pure square terms and a constant term on the other side. That's what a paraboloid looks like. We've also encountered the term ellipsoid, and now we've encountered this term hyperboloid. Okay. And of course, the classic example is in 2 dimensions when you have a hyperbola, and that's where you would have, just like, let's say, one term of this first type. And of course, we can. So something I should have said is that we can write it in standard form by writing it like this. We have that group of terms, then we have minus this next group of terms, which is um plus 1 squared over am plus 1 squared up to ur squared over a r squared, okay, equals 1. So that's just because with positive coefficients, you can always write any positive number in the form 1 over the square of something. And that's a standard thing to do. Okay, well, the classic example of this is just when both groups have only one term, like x squared over a squared minus y squared over b squared equals 1. That's the thing you're used to from 2 dimensions. That's just a hyperbola. So a hyperbola is a special case, a special example of a hyperboloid, where both groups of terms just have one term in it, in each group. Okay. So anyway, you're sort of used to this. What does the geometry of a hyperboloid look like? Well, it's a bit complicated in higher dimensions. Right? In 2 dimensions, when both groups have only one term, it's pretty simple. We just have like 2 disconnected branches. You've all seen the graph of the hyperbola. But in higher dimensions, even in 3 dimensions, there are several different things that could happen, depending on basically how many terms are in each group, how many terms are in the group with positive coefficients, and then how many terms are in the group with negative coefficients. You'll get different behaviors. So we're going to look at how that works out in 3 space. We're basically going to have 2 possible shapes in 3 space, and I'll just draw you pictures of those for now. We'll look at the details in a few minutes, but just so that you're aware of what's going on, like there's this shape that looks like a smokestack, like a smokestack from a nuclear power plant. And actually, literally, that's true. They designed smokestacks in the shape of this type of hyperboloid. This is called a hyperboloid of one sheet. And they call it that because it's all connected. It's one connected piece. You can get from any point on that surface to any other point by riding along that surface in some way. Okay, and then but then there's another one which looks kind of like this. It has 2 bowl-shaped things that don't touch. So 2 disconnected pieces. Of course, this one goes up indefinitely and this one goes down indefinitely. Just like this one continues this way indefinitely and also that way. But that's called a hyperboloid of one sheet. Oh, sorry, 2 sheets. Because it has 2 connected components. Right? On this branch, if you want to call it that, any 2 points can be connected by a path that never leaves that branch, and same over here. Right? But you can't get from one branch to the other by a continuous path that stays entirely on that hyperboloid. So those are the two types of shapes that can happen. Okay, and we'll see in a couple of minutes, like, when do we get this behavior and when do we get this behavior? And why can't there be any others? Any other kinds of hyperboloid in 3 dimensions? Okay, so that's all coming in a moment. But let's just take stock of where we are. Okay, well, one thing we still have to do, like in every other case that we've discussed so far, like the paraboloid and so on, we've talked about trace families as a way of understanding the shape, or at least gaining some information about the shape, right? And it's no different here. You see, if I set all of these variables equal to 0, all of these, then you just get an ellipsoid in dimension m, because all the terms will have positive coefficients. So by looking at a particular trace in some m-dimensional subspace of R space, we get exactly an ellipsoid. And actually, you can set these not just equal to 0, but to any constants you like. That will just absorb into this one. Whatever, if you set this equal to some constant and this one, then you can take that entire constant and move it over to the other side. And then just divide by that new constant again so that you have a 1 isolated on one side of the equation. So you'll get an ellipsoid in every such family, right? And what if you do similarly with the other terms? What if I like set all of these terms to 0 or to some constants? Okay, well, if I set them all to 0, then you get the empty set. Because you see that all that's going to be left is just these negative terms, and then there's a 1 on this side. So a bunch of negative terms or non-positive terms can't add up to 1. So it's possible for certain traces to be the empty set. Okay. But if you take u1 to be some large constant, and u2 to be some large constant, and um to be some large constant, then you might get a very large positive number here, which when subtracted from 1 gives you something negative. And then all of these negative terms can equal a negative constant. So that would give you an ellipsoid again, because you see that you would then divide both sides by -1, and you would end up getting a bunch of positive square terms equal to a positive constant, which would be, again, an ellipsoid. So you can start getting some sense of what the trace families... The way that we can understand the hyperboloid is in terms of ellipsoids. The ellipsoid is very easy to understand, because all of its traces are ellipses. And as for the hyperboloid, we can try to understand its shape by just in terms of ellipsoids, by realizing that many of the trace families are ellipsoids, or the empty set. Okay, like let me show you an example of a case where if I take a trace in this plane, I'll get an ellipse, which is a special case of an ellipsoid. Right? Same thing down here. However, if I... Oops, I'll do that in yellow. Okay, however, if I slice a plane through right here, then the trace is the empty set. Right? Now, that doesn't happen here. Here, in this picture, if I slice through here, I'll always get an ellipse. Right, an ellipse, which is a special case of an ellipsoid. Every single time. Okay? So, yeah, if you understand the shape of an ellipsoid, then you can use that understanding to gain insight into the shape of a hyperboloid in that way. Okay, so that... We'll get to more details about 3-space at the very end, where we do our full classification. So I'll come back to these pictures when we do our full classification of the quadratic surfaces in 3-space. But that's roughly all I have to say about hyperboloids, like in the abstract and in higher dimensions. Okay, so that's case 1A3. All right, and that totally covers all the possibilities for case 1A. So what's left? Well, that was the case when Q was different from 0. Case 1B is going to be when Q is 0. Let me write that down here. All right, and we're going to understand that case also in terms of our understanding of ellipsoids. Basically, it looks like this. It's like, again, let's label the coefficients kappa 1, kappa 2, just for simplicity. Rather than lambda J1, I'll just rename that as kappa 1. And then I have a 0 on the other side, because that's the Q, which in this case is 0. All right, so I claim that we can understand this type of set also in terms of our picture of ellipsoids. Okay, this type of set is called a hypercone. Oh, okay, I jumped the gun a little bit. I jumped ahead of myself. No, so we have to make the same distinction, of course, as in the last case, where we have to worry about what happens when all the kappas are positive. All the kappas are negative, or let's say the first m of them are positive, and then the last r minus m of them are negative. This is after a permutation of the axes. Right, so to relabel the variable so that it's the first m of them that have the positive coefficients. And there's no loss of generality. This is without loss of generality. And that will cover all the cases under 1b. All right. Well, how does it work out? So if you see that if the kappas are all positive, then the whole graph is just a singleton set. Namely, the whole graph is just the origin. Okay. I forget exactly what we're calling this graph at this point, because it's undergone several transformations from the original S. You'll remember that we then wrote that as the image of some set T under a rotation, and that was the image of U under a translation, which was the image of V. I don't even remember under what, but the point is that the quadratic hypersurface whose equation is this. I don't really have a name for it at this point. I stopped naming things a while back. But that just turns out to be this. a singleton set consisting of just the origin in R space. Okay, and why is that? It's because since the kappas are all positive, every one of these terms is non-negative. So you have a sum of non-negative quantities equal to 0. Whenever that happens, then every term has to be 0. So the only solution is u1 equals 0, u2 equals 0, ur equals 0. And that point is just the 0 vector. So the 0 vector is the only solution point of the equation. And so that's a very trivial case, just a singleton set, a one-point set. Counts as a kind of degenerate case under 1b, in particular 1b1. All right, if all the kappas are negative, all of them, then it's the same analysis. It's also the singleton set consisting of just the origin. Okay, and that's simply because then every term will be like non-positive. If every kappa is negative, and if you have a sum of non-positive quantities equal to 0, then again, all the quantities have to be 0. So, okay, it's clear that this works. All right, well, those don't count as hypercones. That's why I had to pull back on what I said. Now, the hypercone is this case, 1b3, where you have at least one positive kappa and also at least one negative kappa. Right? And we can, again, subdivide those into groups in this way. So, yeah, in more detail, slightly more detail, 1b3 looks like this. You'll have these terms here with all positive coefficients. And then you can set that equal to like the absolute value of kappa m plus 1 times u m plus 1 squared, right, all the way up to, I don't have quite enough room to write it, so I'll break it down here. Absolute kappa r times ur squared. So that's just like where I took the terms with the negative coefficients. You can write any of those, take any of these negative coefficients, you can always write that as minus its own absolute value. And then I'm just moving all those terms to the other side of the equation. So I'm leaving over the terms that have the positive coefficients, and then taking all the terms that have the negative coefficients and just moving them over to the other side as positive terms. And so then I get this equation. And also on this side, it's all positive coefficients. Okay, and you have at least one term on each side. But notice that there's no constant term. The constant term is 0. Oops, I don't know how that happened. All right, so that's what the equation of a hypercone looks like. And so let's look at a very simple example of this in 2 space. You have to have one term in each group. So you can have something like, let's say a times x squared equals b times y squared, where both a and b are positive. Right? And after dividing through by b, let's say, we can write it as y squared equals a over b times x squared. And a over b is positive. And then you can just take square roots on both sides, and you end up with this. So what this breaks down into 2 lines, you see. You have the line y equals, this constant times x, which is some line through the origin of slope square root a over b, and then you have y equals minus square root a over b times x. So you see that the 2 slopes are mutual negatives, and both lines pass through the origin. So you get this like x, like what I call figure x. It's the union of 2 lines, 2 intersecting lines. Okay. So that would count as a hypercone, and actually we just call it a cone. But this is maybe a little unfamiliar to you because you're used to a cone in 3 space. Maybe you've never thought about the analogous concept in 2 space, but this is it. Okay, so again, the key to understanding the shape, the geometry of a hypercone is the ellipse, the ellipsoid. Okay, because you see that there are certain natural coordinate subspaces that we can look at. If I, for example, set um plus 1 to be 0, and um plus 2 to be 0, and ur to be 0, so I'll just get a 0 on this side. Right? And that's just, because these coefficients are all positive, that's just the one-point set. Right? But if instead of plugging in 0, I just plug in certain constants, let's say, um plus 1, I just substitute that, some constant for that, and some possibly different constant for the next variable. So then this whole side will just be one big constant. And if that constant is different from 0, perhaps, it doesn't have to be, but it could be. And if that constant is different from 0, then you see what you're getting is exactly an ellipsoid in m dimensions. Because you have all positive coefficients here, pure square terms, set equal to some non-zero constant. By dividing through by that non-zero constant, you can get a 1 on that side. And so you can understand those m axes, u1 through um, like the trace in that subspace, or anything parallel to it. Right? So it doesn't just have to be that coordinate space, the span of the first m axes. It could be any space parallel to that. because the remaining variables don't have to be assigned the value 0. They could be assigned any values you like, any constant values. So basically all spaces parallel to the space spanned by the first m axes. We fully understand the traces. They're just ellipsoids or single point. You see where the single point is. For instance, here you have a 1-point intersection. Whereas here you have a 2-point intersection, which counts as like a one-dimensional ellipsoid. The union of, or the doubleton set consisting of those 2 points counts as a one-dimensional ellipsoid. So most of the traces look like that, but you see that there's this one trace right here where the intersection point is a singleton set. And if you think about a cone in 3 dimensions, it's similar. Right? Think about a cone in 3 dimensions. We mean like a double-napped cone, because it has to go indefinitely in both directions. So like if you slice through this way, you'll get an ellipse, but if that plane is of a certain special height, namely the height of this vertex of the cone, then the whole intersection set will just reduce to a 1-point set, which is what happens when you have pure square terms with all positive coefficients set equal to 0. So it's just going to depend whether this constant comes out to 0 or not. If it is, then you get the 1-point set. If it's not, then you'll get an ellipsoid in m dimensions. And of course, the same can be done with on the other side. Instead of setting u sub n plus 1 and all the rest of them to be constants, I can set u1 to be a constant, and u2, and um. And then you see the same analysis applies, because on the other side, all the coefficients are positive. So if this whole side reduces to some constant, you'll have 2 cases depending on whether that constant is 0 or not. And then you'll either get a 1-point set or an ellipsoid. So you see that the shape of the ellipsoid is really the key to understanding the geometry of a lot of the other possibilities by considering various trace families, or sort of the intersection of the entire quadratic hypersurface with some special subspace, let's say spanned by some subcollection of the axes. And that will turn out to be an ellipsoid. So if you understand how to draw an ellipsoid, or roughly what it looks like, or what its properties are like, it throws light on what the hyperboloid understudy looks like, or what the hypercone understudy looks like. Okay, so that's the case of the hypercone. Okay, very good. So have we covered all the cases then? Yes, we have now. So we don't really have a complete description, obviously, of any of these surfaces, hypersurfaces. We just have some insights about them. Okay. Now there is one additional thing I really wanted to say about ellipsoids. Yeah, there's an important property of ellipsoids. I'll just mention briefly, which is the in-sphere and circumsphere. And then the radius of this is called the in-radius, and this one has a circumradius. Okay, so let's consider the case of an ellipsoid in r dimensions, just to be consistent with the prior notation. In standard form like this, where all the kappas are positive. Strictly positive. Okay, we can write it, of course. Kappa 1 can be written like that, and so on, but let me not bother with that notation because it's not really relevant. All right. So I claim that there is a sphere centered at the origin, just tangent to the ellipsoid, and then there's another sphere also just tangent but outside. So like one sphere is inside, just touching like the inside surface of the ellipsoid, and then the other sphere is outside and just touching. And we can calculate these radii. They're interesting formulas. And we can also figure out exactly where the points of tangency are. So, in 2 dimensions, it's not surprising that, okay, this is not the best picture. Okay, it's not too surprising that the in circle, we would call it that because it's a circle, has radius equal to the minor axis. Let me call that rho. And then the circumcircle has radius equal to the major axis. And let me call that capital R. Okay, and then the points of tangency are exactly the points where the original ellipse touches the axes. Right? The original ellipse cuts through the axes precisely at those points of tangency. Okay, now this is a very general situation in higher dimensions with an ellipsoid. We can look at a picture in 3 space. An ellipsoid in 3 space looks something like this, where it has elliptical cross sections, possibly of different shapes. Okay. Whatever. And you can see that like there's going to be an inscribed sphere. And also a circumscribed sphere. And again, the points of tangency are like exactly on the axes. On the original ellipsoid and also on the axes. Let's say there and there. Okay. So what's going on here? Like where are these things coming from? And also how do we determine the radii? I'll always call the in radius rho, and I'll call the circumradius capital R. Okay, well, in standard position, it's really not the biggest deal. We can say immediately what the in radius and circumradius are. The in radius is just going to be the smallest semi-axis. Right? And so let's recall what the semi-axes are. A1, remember, was the square root of 1 over kappa 1. A2 is the square root of 1 over kappa 2, and so on. Okay, and we can also, because the square root function is increasing on its domain, right? The square root function is an increasing function on the non-negative side of the real line. So we can basically take the square root out and say that's the square root of the minimum of the reciprocals. Okay, and then notice that the reciprocal function is decreasing on the positive side. So we can also like put the reciprocal outside, but change min to max. And that allows us to express the answer purely in terms of the kappas. You just take the maximum of all the kappas, take its reciprocal, and then take the square root. And that's going to give you the in radius. Okay, and similarly, the circumradius will be, you'll just take the minimum of the kappas. And then it's clear also where to locate the points of tangency. Wherever the maximum is attained. Basically, so like, let's say kappa 3 happens to be the maximum kappa. Well, then the point of tangency with the in-sphere is going to be attained on that third axis, U3, the U3 axis. Okay? And if, let's say, kappa 7 happens to be the minimum of the kappas, then the points of tangency with the circumsphere, this one, will appear like on that axis. Okay? And actually several axes could give points of tangency because the kappas some of the kappas could be tied for minimum, or some of the kappas could be tied for maximum. So for example, if let's say both kappa 1 and kappa 3 are the max of all the kappa j's, then the U1 axis and the U3 axis will both have points of tangency with the in-sphere. Okay? So anyway, it's not a big deal, like finding the in-radius and also finding the circumradius and seeing where the points of tangency are. But the really amazing thing about it is that we actually can find these without knowing the kappas at all, just from the original equation, before we did any of the transformations. You see, actually, you know what? I want those. Okay, so you have to remember that the kappas were just expressed in terms of the original eigenvalues and then the constant q. And then so, 1 over kappa 1, or its square root, can also be expressed this way. So, back from the original equation even, well, is that really right? Where did the constant q appear for the first time? I guess we first had to do a rotation and then a translation. But the point is that from an early stage, we didn't have to reduce all the way to this standard position. We could have found these constants, like A1, directly from knowing the eigenvalues of the matrix, capital A, that the quadratic form was based on, and then the constant q. And then, by taking the min or the max of those, you can find the in-radius and the circumradius. So that the ellipsoid doesn't have to be in standard position for us to be able to find or calculate the in-radius and the circumradius. Okay, so anyway, that's something I wanted to mention. And now we can finish off this video by just doing the actual classification in dimensions 2 and 3. Okay, so let's do dimension 2 first, because it should be fairly easy. And we're just going to look at all the possibilities for a quadratic. Oh, you know what? Before I say this, there is one more point, which is that, like, you may wonder if it's possible to have some quadratic equation and do some transformations to it in such a way that all the quadratic terms eventually drop out. And the answer is no, because of this theorem that if A is a symmetric matrix and 0 is its only eigenvalue, then in fact A must be the 0 matrix of size d by d. So there's only one symmetric matrix that has 0 as its exclusive eigenvalue of multiplicity d, meaning that this has, I'm assuming that the matrix has all of its eigenvalues equal to 0. So the multiplicity of that eigenvalue is exactly d. Another way to put that is that the characteristic polynomial would be t to the d power. So it has 0 as a root, exactly d times. So the symmetry of the matrix and the fact that its characteristic polynomial is t to the d power, those two things together is enough to imply that the matrix is just the 0 matrix. Okay, you see, if we didn't know the symmetry, then this wouldn't be possible. There are matrices that have this characteristic polynomial that are not the 0 matrix. Right, but there can't be any symmetric matrix that has this as its characteristic polynomial, other than the 0 matrix. Now, the relevance of this for us is that we started out by assuming that A was not the 0 matrix. Because A was the matrix that our quadratic form was based on, remember? And in order to have a genuine quadratic, we assumed that we assumed that at least one of the entries, at least one entry of the matrix A is non-zero. So A, in other words, is not the 0 matrix. Okay, and it is symmetric. It is symmetric by assumption. So those two things together show that 0 can't be the only eigenvalue. Now, why does that matter? Well, that matters because if you look at the diagonal matrix D, that has the eigenvalues on the diagonal. So this is not the 0 matrix, right? Because there's at least one non-zero eigenvalue. Let's say lambda j, whatever. Right? At least one of these entries is not 0. So this is not the 0 matrix. Okay, and that means that after the reduction, the quadratic form will have at least one pure square term, namely this one, like lambda j uj squared, or whatever. After we finish our reduction process, there will at least be one pure square term. There must be. So it's impossible for this reduction process to be applied to a genuine quadratic equation and then yield like a linear equation as the result. There must always be a square term that pops out of it at the end. Okay, and that it just follows from this theorem. Now, why is this theorem true? Okay, well, it's actually very easy. It just follows from the principal axis theorem. Principal axis theorem. Okay, so the principal axis theorem implies this because remember that the principal axis theorem ensures... Oh, I'm sorry. I'm misquoting. No, I mean the spectral theorem. It follows from part of the spectral theorem. Because remember that part of the spectral theorem ensures that every symmetric matrix, real d by d symmetric matrix, is orthogonally similar to a diagonal matrix. Okay, and it's this diagonal matrix in particular. It has the eigenvalues of A on the diagonal. So if I assume that 0 is its only eigenvalue, right? If I'm making the assumption here that A is symmetric, so therefore the spectral theorem does apply, right? Because the spectral theorem only applies to a symmetric matrix. So I'm using that just to be able to apply the spectral theorem. Okay, and then I'll also use this, that 0 is the only eigenvalue, to say that in fact all the lambdas are zeros, so that D is the 0 matrix. But now you see what happens. Any product of matrices in which one factor is the 0 matrix will have to equal 0. So it's going to force A to equal 0, which is exactly the conclusion we want. Okay, so that it's an easy application of the spectral theorem. Now, one question that this leaves unanswered is, so, okay, all symmetric matrices that have exclusively 0 eigenvalues, there's only one of those, the 0 matrix. But can we have a non-zero matrix that has 0 as its only eigenvalue, but is not symmetric? How do we come up with that? Okay, so there are numerous examples of that. Anyway, I think I'll just leave that aside, and let's move on to our classification. Okay, so in 2 dimensions, we can just jump right to all the types. We should really start by just writing down like what the general quadratic equation in 2 variables would look like. So it has 3 quadratic terms. And here A, B, and C are not all 0, so that there's at least one quadratic term. And then you'll have linear terms. Let me write them like this, and then you'll have a constant term set equal to 0. So that's the general quadratic equation in 2 variables. But, after our reduction, we can eliminate the cross term by a rotation. So just ignore that term. Of course, when you do that, the coefficients will change. The coefficient of this quadratic term and this one will change, but I'm not going to use a different notation. Just to save on different notations, I'll just repurpose the letters A and C to denote the coefficients in the new transformed equation after the rotation. And similarly for all the other letters. Okay, so yeah, the A and C appearing here are not the same as the A and C appearing here, but they're just really placeholders for certain constants. So that's fine. All right, so after a rotation, we get that. Okay, also, if A is not 0, then we can complete the square and absorb the linear term into the quadratic term in X. And if the C is not 0, then we can do similarly with that term. We can absorb the term Ly into that, okay? So there's only a certain small number of possibilities for what the resulting equation can look like. Basically, you can have two quadratic terms that are both present, so no need for linear terms, right, where a and c are both non-zero. We might have one quadratic term and one linear term involving different variables, where the a is really present. But you see, this would be the case where c is 0. So you still need the ly term because there's no quadratic term in y to absorb that into. Okay, plus p. And by the way, the p changes, of course, right? When you do the absorption of kx into that, the p will change because of completing the square. But I'm still using the same letter p for the constant term, just to save on different notations. Right? And here, also L is non-zero. Oh, sorry, no, L could be 0, or it could be non-zero. So, and now, of course, there's also the case where you have the quadratic term in y and the linear term in x. But I'm going to ignore that because these two cases are very similar under a permutation of the variables. So one way to cut down on cases is to permute the variables so as to cover similar cases all at once. Okay, so the case where you have one quadratic term and one linear term and one constant term can be just regarded as one case. And this is like a standard example of it where the x appears quadratically and the y appears linearly. But could, of course, swap those as well. Okay. Now, are there any other possibilities? No, there aren't, because by the theorem we just proved here on this page, see, this a and c are exactly the eigenvalues of the original symmetric matrix. The original symmetric matrix would have looked like this. And by a, b, and c, I'm referring to these original coefficients. But after the reduction, you're left with a diagonal matrix where you have like the eigenvalues. And I'm just renaming those as a and c. That's like the new a and the new c. But those are exactly the eigenvalues. And remember, we just proved that for the original matrix, because it's not 0 by assumption, right, because these three numbers are not all 0, its eigenvalues can't both be 0 either. Can't have all 0 eigenvalues. That's what we just proved. So therefore, a and c cannot both be 0. And therefore, they're either both non-zero, or maybe one of them is 0, and the other, in that case, the other must be non-zero. Okay, but yeah, these are the only possibilities so far. But of course, these can be split further into various other possibilities. Like, for example, this case can be split into the case where L is 0 versus the case where L is not 0. Right? If L is 0, then you're just getting this equation. Okay, and what is the solution of that equation? Well, you can solve it explicitly as long as the signs cooperate. Right? So actually, there's still various possibilities. One possibility is that if a and p have opposite signs, like the product a times p is negative, or at least less than or equal to 0. In that case, then you can move the p over and say x squared is like minus p over a, which is a non-negative quantity, and then you can take square roots. And you'll find that you just have the following solutions. X is plus or minus radical negative p over a. So there are basically either two solutions or one, depending on whether p is 0 or not. Okay, and notice that y is unconstrained. In this equation, y does not appear. So this equation is cylindrical with respect to y. And what that simply means is that when x takes one of these two values, y is arbitrary, so you get a vertical line. And then when x takes the other of the two values, you get another vertical line. Now those two vertical lines can coincide if p is 0. So you see already we have two cases coming out of this. It's either like a double vertical line, meaning the two vertical lines kind of coincide with each other. So it's really just one line, but to make it quadratic, you have to count that line twice, basically assigning a multiplicity to that line. And that one line has a multiplicity of 2. That's what happens when p is 0. You basically just get the line x equals 0, but you have to count it with multiplicity of 2, because the equation really is x squared equals 0. So it really has 0 twice as a root. Right? X squared equals 0 has 0 and 0 as roots. So you have to count the line x equals 0 twice. So we call that a double line. Okay, that's one degenerate case of a conic section. And the other case where p is not 0 is where you have just two vertical lines, two separate distinct vertical lines, a union of them. It's the union of two distinct vertical lines. Okay. Now, of course, don't forget that there's a very similar case where it's the y squared term that's going to be the one left, and those are going to be horizontal lines rather than vertical lines. So the crucial feature here is not that they're vertical, it's just that they're lines. It's like a pair of parallel lines, the union of them. Or a single line, but counted with multiplicity of 2. Those are two like degenerate cases. Now, of course, there's the other possibility is that a times p is strictly positive, and we don't have to spend very much time on that case. If a times p is strictly positive, then when you move the p over, x squared equals minus p over a, that has no solutions, because it's x squared equals a negative. So the solution set there is just the empty set. That's also kind of a degenerate case, right? In other words, the empty set can occur as the graph, even if the equation makes perfect sense and satisfies all the constraints. Like a is not equal to 0, so there's at least one quadratic term. So like a typical example of that type of thing would be, let's say I just have this equation, and I ask for the graph in 2 space. Well, the graph is empty. Okay, so good. But it's a legitimate quadratic equation because it has like an x squared term, and then a y squared term, and an x term, right? Just with a lot of 0 coefficients. But the constant term is -1 on the other side. So it certainly fits the bill, it fits the form. But the solution set happens to be the empty set. So we have to count the empty set as a degenerate case as well. Good. Now, so that covers the case when L is 0. What about the case when L is not 0? Then the y term is actually present, and we can isolate it. Right? We can rewrite the equation with y isolated, and then y is going to be solved for as some quadratic function of x. Right? In detail, it's like minus a over L times x squared, and then minus p over L. But let's just rewrite it as alpha x squared plus beta. Okay, and we know what that is. This alpha is not 0, because the a is not 0. And all we did was divide through by L. So a over L is certainly still non-zero. And we know what that is. That's a parabola. So that's the case of a parabola. Okay, and that covers all of those cases under this column here. But it still remains to analyze this column here, when you have just two quadratic terms, no linear terms at all. Okay, and let's do that on the next page. Okay, so yeah, the first thing we can do is like put the negative p on the other side. And again, we have to split the case when p is 0 from the case when it's not. Okay, when it's not 0, we can divide through by that, and you'll have like a over p times x squared, and then c over p times y squared, and you'll have a 1 on this side. Okay, but in this case, you just have this. And we've already sort of dealt with that equation before. We can basically just isolate y squared. Right, and now everything depends on like the signs of a and c from here. If a and c have opposite signs, but notice that both a and c are non-zero. I should have said that here. Both a and c, both non-zero. So they either have the same sign, they're both positive, or they're both negative. They either have the same sign that they're both positive, or they have the same sign they're both negative, or they have strictly opposite signs. But neither one of them can be 0. Well, if they have opposite signs, then the constant negative a over c will be a positive constant, and we can take square roots on both sides. Right? And so what do we get there? We get y equals plus or minus the square root of that positive constant times x. And we know, we talked about this already, what this is a union of two intersecting lines, which is just called a cone in 2 space. So that's another case. You can consider it a degenerate case. That's a sort of a subjective term. But you'll see that like in the 3-dimensional classification, we don't want to consider a cone to be a degenerate case. A cone is considered one of the big main cases. And so we probably should consider a cone also to be one of the big main cases of a conic section as well. But there is an argument for considering it to be degenerate, which is something like this. If you look at the classic picture of the double napped cone and then a plane slicing through. So, you know, in the case of the elliptical cross section, when you push this plane down continuously, there comes a single critical moment where the ellipse reduces to a 1-point set. But it only happens at some critical moment in that continuous process. Whereas the ellipse is like stable. If you take the ellipse picture here and just perturb that plane a very tiny amount, either up or down, it will stay an ellipse. Okay, but this singleton set is unstable. If you perturb that plane up or down even a tiny bit, you don't get a singleton set anymore, you get an ellipse. And see, the same is true of that the crossed lines, because the crossed lines occur in this plane that passes through the vertex. And if I perturb that plane sort of right or left, even a little bit, those go away, and you get a hyperbola cross-section. So in that sense of stability, it really is right to consider this to be a degenerate case. Okay, anyway, there's still another case under here, which is where a times c is positive. They have the same sign. And then you see that the solution set is just the empty set again, because y squared is greater than or equal to 0, but this would be a strictly negative constant, and then this x squared is greater than or equal to 0, so this whole thing is less than or equal. Oh, so sorry, I'm wrong. It's not the empty set, just the origin. It's just the singleton set, because if x and y are both 0, then that equation is solved. That equation is satisfied. But that's the only solution point. So yeah, we have the singleton set again. All right, and that totally covers that case. Now, what about the rest of this case in here? So again, that's going to depend on the signs. Right? We know that both coefficients are non-zero. And so there are 3 possibilities. They're either both positive, they're both negative, or one positive and one negative. And of course, that breaks down further into 2 cases, where like it's the first one that's positive and the second one that's negative, or first one that's negative and the second one is positive. But since those 2 are similar under a permutation of the variables, you know, we'll just analyze one of them. Right? And everyone already knows what this is going to be. When they're both positive, then clearly you get the ellipse case. When they're both negative, you get the empty set, because this side will be less than or equal to 0 if both coefficients are negative, and yet this is strictly positive, so can't be equal ever. And then if one is positive and one is negative, you get a hyperbola. All right, so that's it. That's the entire breakdown. We now know every single conic section that can appear and when it appears. We have a kind of hierarchical classification scheme. All right, so the big families are the ellipses, the hyperbolas, and the parabolas. But we also have the following possibilities. We have like a line of multiplicity 2, a union of two parallel lines, a union of two intersecting lines, a singleton set, and the empty set. All count as conic sections. Okay, and those are the only conic sections that can occur. All right, well, the same exact classification can be done in 3 dimensions. And let's just jump right to like the canonical forms. Let's just see how it would go. So after all the reductions are done, right, you're either going to have 3 pure square terms and a constant term. I mean, let me put the constant term on the other side, just for convenience. It doesn't really matter. I could write it as minus p. I'll do that. Okay, where, again, a, b, and c are all non-zero. We could have, let's say, 2 quadratic terms and a linear term, and I'll just keep calling the coefficient c, just to save on notations, you know. And here a and b are non-zero, but c could be 0 or not. And you'll get different behaviors, right, in those cases. You could also have just 1 quadratic term. So let's say something like ax squared plus by plus cz equals minus p. And here a is non-zero. B and c, though, could have a number of possibilities, right? They could both be 0. We could have, let's say, b non-zero and c equal to 0. B equal to 0 and c not equal to 0. Or they could both be non-zero. Okay? And those cover all the possibilities. Each one of these, of course, has subcases. But that covers all the possibilities at the level of analysis we have engaged in so far. Because you can't have no quadratic terms. So you either have just 1 quadratic term or 2 or 3. Okay? That does cover all the possibilities so far. All right, now in this case here, this first one, we also need to distinguish the case where p is 0 from the case where p is not 0. And when p is not 0, we can divide through by negative p and just absorb the 1 over minus p into the coefficients. And that's going to give something like this. Oh, I'm sorry. No, I divided by negative p, so I'll get a 1. Yeah. Okay, and in this case, we have this equation with a 0 on the other side. Okay, so if we look at this one, everything now depends on like the signs of a, b, and c. So there are a number of possibilities. If they're all positive, then you clearly have an ellipsoid. Okay, if they're all negative, then you have the empty set. What else can happen? Well, let's say, you know, a and b are both positive, but c is negative. So that's a hyperboloid. But also if a is positive and then b and c are both negative, that's also a hyperboloid. The question is, what kind of hyperboloid? These two hyperboloids should be different in some way. And this is where, remember, I mentioned like the hyperboloid of one sheet versus the hyperboloid of 2 sheets. So I want to delve into that in slightly more detail, just to see what the distinction is. Okay, but that will cover all of those cases, because, you know, the other possibilities are just permutations of these. Like, for example, a and c could be positive while b is negative, but that's just a permutation of a case we've already covered. So the essential geometry is already here. All right, so let's take a quick look at that. If I have this equation where, let's say, a and b are both positive and c is negative, what can I say about it? All right, well, you can see that if I set z equal to a constant, any constant whatsoever, let's say k is completely arbitrary, then the equation will boil down to this. I'll move this term over, and remember that I'm setting z equal to k, so here I have like c times k squared, and I've moved that term over. But remember, c is negative, which means that k squared is non-negative, c is negative, so this whole thing is like less than or equal to 0, but with the extra minus here, it's greater than or equal to 0, and so you get some constant over here, which is at least 1. It's 1 minus c k squared, but that's like at least 1, since this term is non-negative. Okay. What should I call that constant? I don't know. Q. So, but the point is it's not 0. So when you divide through by q, you will get an ellipse, an elliptical cross-section. So you see that in every horizontal plane, every plane of the form z equals k, which in 3 space is just some plane passing through the point k on the z-axis. So it's parallel to the xy plane. Every single plane parallel to the xy plane cuts through that figure, this hyperboloid here, in an ellipse. Okay. Now, what about the other trace families? Like, what if I set x equal to a constant? Well, that will be a hyperbola, obviously. So if you set x equal to a constant, this term is going to be absorbed into the 1, but the b and the c differ in sign. So that equation is going to have the graph of a hyperbola. So you see that like 2 of the 3 trace families have hyperbolic cross-sections, and then the third trace family always gives an elliptical cross-section in every single height, at every single height k, with no exceptions. And that's the hyperboloid of one sheet. So when you have 2 positive coefficients, that's the case when you get the hyperboloid of one sheet. And when you have just 1 positive coefficient, but 2 negative coefficients, then you get hyperboloid of 2 sheets. And I'll leave that analysis to you, since this video has gone on way, way too long already. What you should look for is when you look at the horizontal trace family in planes of the form z equals k, you'll see that for certain values of k, like large enough positive or large enough negative, you will get elliptical cross-sections, but when k is between, like close to 0, you'll get the empty set. Okay, so you see what it looks like is like you'll have elliptical cross-sections at high enough heights and also at low enough heights, but just the empty set as the cross-section in the middle. And then there's actually 2 special heights where you get singleton set intersections. So I'll leave that to you to analyze. But that covers all the cases under this form here. Now what about this form? Okay, so again, we have to go through the analysis of the different cases, but it's not difficult. Right? So for example, if A, B, and C are all positive, then it's a singleton set, the graph. If A, B, and C are all negative, it's also a singleton set. Okay, that's simply because if all 3 terms are non-negative and their sum is 0, then every one of those terms has to be 0. Similarly, if all 3 terms are non-positive and their sum is 0, all 3 terms have to be 0 individually. So there's only one solution point, namely x equals y equals z equals 0, the origin. Okay, what else can we have? Let's see. Under this case, we can also have, let's say, 2 coefficients positive and 1 negative. And so then we would move the negative term to the other side, and that's going to give us a cone. That case gives us a cone. But of course, the other case gives us a cone too. Simply because, you know, the 0 on this side of the equation here, this 0 right here, means that like the absolute sign of every term is unimportant. You can always multiply through by -1. So, you know, these 2 cases become very similar just by multiplying through by -1. They both give you a cone. Right, why do they give you a cone? Let's take a little bit of a closer look at that. So let's say I have ax squared plus bx, or plus by squared plus cz squared equals 0, and I'm going to assume that c is negative while these are positive. So we can move that term over and write this as like the absolute value of c. And then I'll just divide through by that. So to isolate z squared. Okay. And you see that now both coefficients are still positive. Right? So what is it that makes that a cone? Right. Here's what it is that makes it a cone. Basically, if I look where y is 0, so that's just the xz plane. If I look just exclusively in the xz plane, that will make this term drop out. That term will become 0. And so then you can just take square roots on both sides. And what you'll get is one of those z equals plus or minus some constant times x, which is a pair of crossed lines. So you see that the intersection in that plane is just a pair of crossed lines. Oops. And the same will be true with the xy plane. If you look, not the xy, the yz plane. Look in the yz plane. Similarly, you set x equal to 0. You'll get also like a pair of crossed lines as the trace. Okay. And then what about setting z equal to a constant? Well, if I set z equal to a constant, then I'm clearly getting the equation of an ellipse, because I have a positive coefficient times x squared, and then another positive coefficient times y squared equals a constant. Oh, so and that constant, notice, is positive because it's z squared. So when you set z equal to any constant, you're then squaring that, and you'll get a positive constant. Except when z is 0. When z is 0, you have a 1-point intersection. Right? Because when z is 0, then so is z squared equal to 0. And then you have like 2 non-negative terms whose sum is 0. So the origin is the only solution. It's a 1-point solution. But otherwise, you'll have an ellipse. And you see the ellipses, the elliptical cross-sections. So you get exactly a cone. Now notice that this doesn't have to be a circular cone, because these red crossed lines don't have to have the same absolute slopes as these green crossed lines. And the ellipse here, as the cross-section, doesn't have to be a circle, because these 2 coefficients don't have to be equal. But there will be some elliptical cross-section. So it's a kind of elliptical cone, rather than a necessarily circular cone. It would be circular when a equals b. Right? But anyway, it is a cone. Great, so that totally takes care of this first column here. All right, what about the second column? So let's see, when c is 0, right, then that z term totally drops out, and what you're getting then is just a 2-dimensional conic section which is cylindrical with respect to z, because z is omitted from the equation. So that just reduces to the 2-dimensional classification. So we're essentially done. You just do a 2-dimensional analysis of the resulting equation. That will give you, that will tell you what conic section this is in the xy plane. And once you know what conic section that is in the xy plane, you just drag that conic section parallel to the z-axis, and it gives you a cylinder. So this is some sort of conic cylinder, conic section cylinder. And again, exactly what I mean by that is that it's a conic section in the xy plane dragged parallel to the z-axis. So it could be like a parabolic cylinder or an elliptical cylinder. Right? Like an elliptical cylinder would have an elliptical cross-section, but just extend up and down forever. Okay? Or it could be a hyperbolic cylinder, a hyperbola cross-section. Right? What about the case when c is not 0, when there is a z term present? Okay, then you can isolate the z term and express z as some quadratic function of x and y. Let's say alpha x squared plus beta y squared plus a constant, which I'll still call p. Right? And alpha and beta are both non-zero. Because they're basically just a and b, well, minus a divided by c, and then negative b divided by c. But since a and b are non-zero, that means alpha and beta are non-zero too. Okay. So what do we get in that case? Well, we get a paraboloid, we know already. We get some sort of paraboloid, but again, there are two possibilities for what type of paraboloid it could be. Right? Just like there was a hyperboloid of one sheet, and also a hyperboloid of two sheets, there are also two kinds of paraboloid, and they're based on whether alpha and beta are of the same sign or of opposite signs. Okay. I don't have quite enough room to write it here, so I'll just say see next slide for further details. Okay, and actually I'd better just take care of that now. Okay, well I guess it's not the very next slide. So if we look at the paraboloid case, something like this, right? We know that alpha and beta are both non-zero. Okay, if alpha and beta are both positive, then when you set z equal to a constant, like let's say I set z equal to k, right? Then I can move the p over, and I'll have something like this. So as long as this constant here is positive, let's say that constant comes out positive, then you'll have an ellipse. The cross-section will be an ellipse. Right? If k minus p happens to be 0, then the cross-section will be a singleton set, because again, both of these terms are non-negative, and they would add up to 0. And then if this constant k minus p were negative, then it would be the empty set. So basically, the constants k divide up into three classes. There's like those constants greater than p. This is in the z direction. So there's like everything greater than p, it forms one class, where you get ellipses. Okay, everything less than p forms a second class, where you get the empty set. And then at p itself, you just get a singleton. So you see what kind of paraboloid that is. It's a paraboloid that has elliptical cross-sections up here, and then no cross-section at all down here. And then there's just a singleton set, right? Oh, like a local minimum. Actually, it's a global minimum, exactly at the point p. So it's like a bowl-shaped. You can think of that, like a special case of that would be a paraboloid of revolution. If you take a parabola and revolve it around its axis. But that's the special case where alpha and beta are equal, so that the cross-section is a circle rather than a general ellipse. Okay? If alpha and beta are unequal, but still both positive, then you'll get some sort of elliptical paraboloid. Okay? So that's the elliptical paraboloid. Let me just come back here and try to squeeze it in here. There's the case of the elliptical paraboloid, and then there's the case of the hyperbolic paraboloid. Right? And the hyperbolic case is when alpha and beta are of opposite sign. Let's say alpha positive and beta negative. Because then the same basic argument will work, but the difference is that, so when you set z equal to k, and you move the p over, because alpha and beta differ in sign, this is always the equation of a hyperbola, except when k is exactly equal to p. So the difference, though, is that like when k passes through the value p, so on one side of p, you're going to get hyperbolas that whose branches point in one direction, and then on the other side of p, you'll get hyperbolas whose branches point in the perpendicular direction to that, because k minus p changes sign when k passes through the value p. So when this is negative, you'll have one type of hyperbola, like, its branches will point in a particular direction. And then when k minus p is negative, you'll get complementary hyperbolas, where the branches point in the perpendicular direction to that. Right? When k is equal to p, so that this constant is 0, then you're going to get the crossed lines. So you can see what the picture looks like. That's the hyperbolic paraboloid. It's paraboloid. And if you just study the picture, like this classic picture, like upward opening parabola in one direction and the downward opening parabola in the perpendicular direction, these vertical traces are hyperbolas, but you see that up above the origin, the hyperbola branches point sort of this way and this way, whereas down below the origin in height, the hyperbola branches kind of point this way and that way. This blue direction is perpendicular to that red direction. Okay. Anyway, roughly speaking, looks like this. Right, and you see that this is quite interesting, that at the height z equals 0, if I take a slice through this picture exactly at height z equals 0, the cross-section is actually a pair of lines embedded in this surface. There's actually a pair of lines exactly embedded in that surface. But if I go anywhere above that, I'm going to get an actual hyperbola as the cross-section. And if I go anywhere below that, I also get an actual hyperbola as the cross-section. Okay, so anyway, that's the distinction there. Now, what about, did I skip anything? Did I skip any cases? What if alpha and beta are both negative? Right? So, this case has also its reversal, where let's say alpha is negative and beta is positive, but those are similar. That would just be a hyperbolic paraboloid again. So we don't have to worry about that case. But what if alpha and beta are both negative? Okay. Well, so in that case, it's basically the same analysis as this case here. It's just that you just multiply both sides by -1. So you'll have like a minus that constant, and then the coefficients will be positive again. So it's also going to be like a bowl-shaped thing, except the bowl is going to be upside down. All right? So yeah, these two cases, when alpha and beta have the same sign, you can consolidate those two cases by just saying alpha times beta is positive. Then you'll get, in that case, you'll get an elliptic paraboloid. And then these two cases here can also be consolidated by saying that alpha times beta is negative. And that's when you get the hyperbolic paraboloid. All right, good. So let's come back to our main roadmap here. We're now totally done with this case as well, this column. All right, what about this last column? So remember that this is one of those cases where by doing one extra rotation in the YZ plane, essentially, we can rewrite this so that it looks like this. It has a quadratic term, and then just one extra linear term, and then some constant, which I can still call minus p. So the b, of course, here is not the same as the b here. I'm just consolidating, I'm saving on distinct letters by kind of repurposing the name b for this. But basically, the w is like part of a set of variables, v and w, that are linear combinations of y and z. V and w are two specific linear combinations of y and z. But we can always rewrite the equation equivalently, like in this form. Right? So that's cylindrical with respect to something, right? The v, it's like cylindrical with respect to that v direction. So definitely in every one of these, every type that fits under this column is definitely cylindrical with respect to at least one direction. Let me, at least one direction of 3 space. So in some sense, those are like all degenerate cases. But nevertheless, we should try to figure out what they look like and how they're organized. Okay, well that's just going to be a two-dimensional analysis, you see? And it's going to depend on, sorry, the case I'm ignoring here, of course, is the case when both b and c were 0. In that case, you can't. Remember that to do that procedure where you find that rotation, you need at least one of the two to be non-zero, which covers all 3 of these cases here. As long as one of the two is non-zero, at least, all 3 of those gray boxed cases are covered by this, noting that it's going to be cylindrical with respect to the v direction, and then parabolic with respect to the w direction, where v and w are just two particular linear combinations of y and z. Okay. But what about the case when there is no linear term at all in this equation here? Just both b and c are 0. That's very trivial. Then that equation just reduces to ax squared equals a constant. And you see that the analysis of that is very similar to the analysis of this thing here. Oh yeah, this thing here in 2 dimensions. You're basically just going to get 2 solutions for x, which can coincide. In this equation, you'll have 2 solutions for x, which can coincide. So it could reduce to a single solution with a multiplicity of 2. Or there could be no solutions. It depends on the signs of a and p, the relative sign of a and p. So you'll either get the empty set as a possibility in that case, or you'll get like 2 parallel planes, x equals a constant, and then x equals another constant. So the union of 2 parallel planes. Or you can get a double plane, like a plane counted with multiplicity 2. Right? So I should notate that somewhere. So in that last column, like the possibilities we encountered are the empty set, we have union of parallel planes, 2. We have a double plane, meaning a plane counted with multiplicity 2. That would be like this equation would count as that in 3 dimensions. Okay, and then there was the cylindrical case. And the cylindrical case is the case where, again, like you can make this reduction, where b is not 0, and also a is not 0. But you see that case is just reduces back to dimension 2, because it's really just a conic section in 2 variables, x and w. So if you go back to the 2-dimensional classification and figure out which conic section that is, you can then just drag that with respect to the w direction of 3 space. Right? Actually, you know what it's going to be. It's going to be a parabola, because w enters linearly while x. So this always has to be a parabolic cylinder. And it so happens in 3 space. It's pretty straightforward. This is definitely a parabolic cylinder. Okay, so you have a number of possibilities. Empty set, union of 2 parallel planes, a double plane, and a parabolic cylinder. Okay. Good. Now, are we done with our classification scheme? Well, yes, we are. We've covered every possibility, right? But I should just mention, like, you might wonder, where would 2 intersecting planes fit into this scheme? Right? Just like in 2 space, we had the case of 2 parallel lines counting as a degenerate conic, but we also had another case of 2 intersecting lines counting as a degenerate conic. Right? Well, actually, the way we worked it out in standard position, the two parallel lines would be like x equals a constant and then x equals minus that constant. So the lines have like a symmetry. Okay, I can't really draw at this point, but actually both of these pictures are really horrible. Let me fix that. So, one case was where you had x equals some constant and then x equals minus that constant, the union of those two. And we also had separately a degenerate case where you had y equals a constant times x and then y equals minus that constant times x. So slopes which are mutual negatives. Right, well, we saw that in 3-space, one of the degenerate cases is like a pair of parallel planes. Say like this one and then this one over here. So there should also be a case in 3-space where we have like two intersecting planes. It's a little hard to draw that. Maybe think of it like this. And they intersect in a line. Okay, and of course planes extend indefinitely in all directions, but that's just some picture that should help you visualize what it is. Okay, is that a degenerate conic? And if so, where did we encounter it in the classification? Okay, we did encounter it, and it's here, in this case. Because you see that if p is 0, if this p happens to be 0, and if a and b differ in sign, then that equation is going to be a pair of crossed lines in the xy plane, and then you drag it in the z direction. And that's going to give you a pair of planes that intersect exactly in the z-axis. Okay, so we did, in fact, encounter that case. It's just that since it was sort of hiding in a two-dimensional analysis. This box here was one of two places where we kind of resorted to the two-dimensional analysis and then said, okay, then you just drag that cylindrically with respect to some direction of space. The other place that happened was here, right, where you have essentially a parabola that's being dragged in some direction. But we knew that was a parabola. The difference with this case is that there are different things that could be, depending on the signs of a and b, and also depending on whether p is 0 or not. So there are actually a number of cases that fit in here, including the case of like two intersecting planes. Okay, so anyway, we've now encountered all of the possibilities for so-called quadratic surface in 3-space. Good. Sorry about the length of this video. I will try to make the next one a lot shorter. Take care, everybody.